In the last part of the video, I might have said something slightly incorrect, so I just want to clarify what I was trying to say. Remember, we were looking at the how do you read the volume of a liquid in a cylinder. So you see that this one was 21.6 milliliters. What I just want to stress that, again, in a measurement, no matter what it is, there's always one uncertain digit. And in that last decimal place, in this particular case, there's usually an uncertainty of plus or minus one high or low. That's, I think that's what I said, but I'm not sure, so I just wanted to clarify that. So that means that this measurement 21.6, an acceptable alternative measurement would be 21.5, or which is one lower than the 6, or one higher than the 6 would be 21.7. So that range, the precision of this measurement is usually in the last decimal place, one high or one low. I think that's what I said, but I'm not sure, so I just wanted to make sure that we were clear on that. So again, we're talking about significant figures, and I think I forgot to mention this as well earlier. I'd like you to watch that video called Powers of 10, which I put a link to on Canvas. It's narrated by a famous actor. I think you'll know his voice as soon as you start watching it, but it's a fun video to watch because it shows you the relative scales of everything from the very tiny to the very large in the universe. So and it's all based on powers of 10, just to give you an idea of the power of the metric system. So continuing our discussion of significant figures, so in that previous measurement, if we recorded the volume to be 21.6, like I said, those are the certain digits, and that's the uncertain digit. But the number itself has three significant digits, or three significant figures. Digits and figures are the same thing. So all the digits in a measurement, including the last uncertain one, are called sig figs. I call it sig figs just for short. So the 2, the 1, and the 6 are all significant. Frequently, we need to know the number of significant figures in a measurement reported by somebody else. So we have to know how to treat zeros in a measurement. The following numbers are always significant. Sometimes zeros are and sometimes they aren't, but any number from 1 to 9, non-zero digits, are always significant. When a zero is trapped, what we say captive, between two other digits, like the year 2002 or the number 2002 would have 4 significant digits because the zeros are trapped or captive, so they actually are significant. Trailing zeros are significant if they are to the right of a decimal place. They have to be to the right of the decimal place. So for instance, the number 1.00 grams has 3. I'm just going to put SF for short for significant figures. When in scientific notation, that's another way to clarify that a trailing zero is significant. So the 9, the 3, and the 0 are all significant. So we would say that measurement has 3 sig figs. These types of zeros are not significant when they're leading zeros. So for instance, if you measured something to be 0.0003 meters, that would only have 1 sig fig, because the zeros are just placeholders. Trailing zeros, like the number 1000, only has, let's say it was 1000 meters, that only has 1 sig fig as well. How can I prove that to you? Well, I could write this number here, 0.0003, in scientific notation is 3 times 10 to the negative 4th meters. And when you write a number in scientific notation, the leading number that's before the power of 10, it tells you how many sig figs are in the answer. So I can show you right here that only has 1. The 3 zeros here are reflected in the power of 10, 10 to the negative 4th. 1, 2, 3, 4. So it proves that those zeros are just placeholders. I can write the number 1000 meters like that as just 1 times 10 to the power of 3 meters. So again, that has 1 sig fig as well, the number 1. So when they're to the left of the decimal place, when they're captive, they are significant. When they're leading zeros, they are not significant. when they are trailing zeros before the decimal, they are not significant. And when they are trailing zeros after a decimal, they are significant. So let me just rewrite this in scientific notation to show you what I mean. The number 3090 can be written in scientific notation as 3.09 times 10 to the third. Again, if there's no decimal place, we're going to view that as not significant, because I can write the number in scientific notation like this, where there's only 3 sig figs, the 3, the 0, and the 9. This number can be written in scientific notation as 8.020 times 10 to the negative 1, 2, 3. We're not worried about units right now. So that number has 4 sig figs, the 8, the 0, the 2, and the 0. So make sure you can do problems like that and understand that there's a good reason why we want to do that. So that has 4 sig figs, that has 3 sig figs. What about numbers in calculated results? How do we treat these? Results calculated from measured numbers are at least as uncertain as the measurement itself. So we're either going to have, when we do calculations, you're either going to do addition or subtraction, or multiplication and division. So when we add or subtract, and the way you treat sig figs in those calculations, arithmetic, is a little different. When we add or subtract numbers, we should round the result to the same number of decimal places as the number with the least number of decimal places, which is the least precise value. So let me give you an example. Let's say you had to add the number 23.3203 grams. You measure that on a very precise balance, so it has 4 decimal places. But on another balance, you added another object that you had, maybe for some reason you had to add to the total mass of, or the original mass of 23.3203. But this one was only measured on a top loading balance, which we are more common in the lab, but they only give you 2 decimal places. So what's the proper way to report the sum of those masses? Your calculator is going to give you 30.7903 grams. However, that is not the proper way to express the mass. You should round the mass. So in this class, when I write about, I often will write it like this, where I'll just put a couple squiggly lines. That symbol means about, equal to. So we'd have to round that to 2 decimal places, 30.79 grams. So why did I have to round it to 2? Because this particular measurement that went into this calculation is only known to the 2nd decimal place. I don't know what's after the 7. So it would be kind of crazy to carry the 0 or the 3, because this number isn't known past this decimal place. So I have to round it off to this number of sig figs. So I look at what's after the 9. If it's less than 5, I just leave the 9 as is. If it's greater than 5, I would round up. So we'll try a few problems like that where we practice some rounding off calculations or exercises. And now when you multiply or divide numbers, it's a different set of rules. It's a little easier to understand, I think. And most of the time you are going to be multiplying and dividing things like unit conversion. So it's easier to keep track of this, I believe. You should round the result when you multiply or divide to the same number of sig figs as the number with the least number of sig figs. How do we do that? So 39.5, let's just treat numbers. I just made up some numbers here. 39.5 times 7.8. You plug that into your calculator, you're going to get 308.1, I believe. Let me do that. 39.5 times 7.8. The calculator shows an answer of 308.1. However, this number here only has 2 sig figs. This number that went into the calculation has 3 sig figs. So we have to round our answer to 2 sig figs. So this is about equal to, now how do we change this to 2 sig figs? We're going to keep the 3 and we can keep the next decimal place. So I'm throwing everything out after the 0, but the numbers that I'm throwing out are greater than 5, so I round the 0 up to a 1, and I have to show that this number is 310, not 300 or not 31, so I have to put a 0 there. That answer has 2 sig figs. And it would be correct to write that in scientific notation if you prefer, 3.1 times 10 to the second. Those are both correctly rounded off answers to this particular problem. If the digit to be dropped, so again, just reviewing this rounding off, if the digit to be dropped, the one immediately to the right of the digit to be retained, so that in this case, that would be the 1, is less than 5, then we should round down. Actually, it's the 8 and the 1 I'm getting rid of. So if it's less than 5, we round down and leave the retained digit the same. If it's more than 5, in this case it was 8, we round up. And then there's a third rule, but it's slightly confusing, I think. So if the drop digit is 5, we round up or down, whichever yields an even value for the retained digit. So let's just say for argument's sake that the answer to a problem was 308.5, for instance. So and we have to round to let's say we have to round to 3 sig figs. If the drop digit is 5, we round up or down, whichever yields an even value for the retained digit. So if we're retaining this digit, it's even. So we would say that that is equal to 308. Let's say the answer to some problem was 307.5. That's a 7. And how would we apply this rule? If the drop digit is 5, we want to round to the 3 sig figs, for instance. If the drop digit is 5, we round up or down, whichever yields an even value. So we'd actually round the 7 up to an 8, so you get 308. Sometimes people forget this, so don't worry if you don't always follow this rule. So I generally just ask students to do the following. If the drop digit is going to be 5 or greater, round up. If it's 1, 2, 3, if it's 0, 1, 2, 3, or 4, then you just keep this number the same. We'll see more examples of that in the future, but if you follow this rule as written, or if you forget to follow it, don't worry so much about it. The following examples illustrate the application of this rule. So let's try this. Here's a number. We want to round this to 3 sig figs. So let's see, the zeros don't count, but we want to keep the 2, the 8, and the 6. So after the 6 is a 7, so that would round up. So that would be 0.0287. I round the 6 up to a 7. This number to 3 sig figs, I want to keep the 1, the 8, and the 3. Do I make the 3 or 4? I do not, because the first digit after the 3 is less than 5, so I just keep that as 18.3. This number here, if we're rounding up to 3 sig figs, so here's an application of that rule. I'm keeping the 6, the 8, and the 7, so the first drop digit is 5. Well, 7 is an odd number, so I want to round up to make that even. So I would round it up to 6.88. Well, if you do it the way that I've normally told people to do it in the past, you'd get the same answer. As I said, if the drop digit is 5 or greater, just round the last retained digit up, so you'd still get 6.88. If you're really following this rule strictly, this number here would be kept at 92.8 because this is a 5 and we're getting rid of it. So this is an even number, so you just keep it as 8. I would say 92.9 is also okay. So I hope that's clear. If it isn't, just please bring it up in class and I will clarify it for you. Let's try a problem like this. This is example 1.7 in your textbook. It's a density problem. Oftentimes, like when we do the density of an egg, you can calculate the density of an object by what's called water displacement. You can measure the change in volume of water when you drop an object into it. So how do we treat sig figs with a problem like this? You're going to do this all the time in this class. So this is rebar, it's just steel used for constructing buildings and things like that. You weigh its mass and it's 69.658 grams. And before you put the liquid in, or I'm sorry, the metal in, the volume here, that initial volume, we'll call it V sub I, is equal to 13.5 milliliters. You drop the rebar in the graduated cylinder, the water level rises up to what's called the final volume, V sub F, and that is equal to 21, 22, a little more than 22. They're saying it's 22.4. That looks reasonable. So what's the volume of the rebar? The volume of the rebar is equal to the final volume, 22.4, minus the initial volume, which was 13.5. And to show this properly, you put it in parentheses with a, like that. I know this seems pretty easy. I hope it does. So that would be, now how do I report my volume? That has one decimal place, that has one decimal place. So it's, your calculator gives you the right answer as far as how to express it, 8.9 milliliters. So the density of the rebar, let me move that up a little bit. The density of the rebar is equal to, by definition, mass over volume. So it's the mass of the rebar, which is 69.658 grams, divided by that volume, 8.9 milliliters. And you would get, now what's your calculator going to give you? 69.658 divided by 8.9. Your calculator spits out a really long number, 7.826741573 grams per milliliter. Your calculator does not understand how to round off numbers. It just is a computer. So that's obviously too many digits. If we only know the volume to two significant figures, this number here only has two sig figs. That one has 5. They're all significant. But according to the rules of how to treat numbers that you are multiplying or dividing, you have to round off this answer to the factor that had the least number of sig figs, which is this one. So I have to round off to 2. So I'd have to round that off to 7.8, because everything I'm throwing out after the 8 is less than 5. That first digit is less than 5. So the answer, the proper way to report that would be 7.8 grams per milliliter. And it would also be acceptable to say that that is 7.8 grams per cubic centimeter. Now you could have done this all in one step and you'd still get the right answer. Whether or not you break it up into 2 steps like this, first calculate the volume and then plug that into the equation for density and solve, that's fine. Some people choose to just do it all in one step, where they would put this in the denominator where the 8.9 is. So that's fine too. I'll show you some examples of that as well.